So procedure, label the variables for what is to be determined and a variable for what is to be maximized or minimized, right? Trying to maximize profit or minimize cost or something. Write an equation for what is to be maximized, minimized. You may have to do some extra work because it needs to be in terms of one variable, right? Take the derivative and determine the critical numbers. Determine whether the critical number represents a max or min. Write a concluding statement with units, if there are any. So the first one is just a number problem, right? Determine two numbers whose product is 4 and whose sum of squares is a minimum. Okay, so two numbers whose product is 4. So we need two numbers. What could they be?
2 and 2
No. We need variables to represent these two numbers.
X and Y.
Sure. So let the numbers.
Well, it does say two numbers, which implies that they're distinct, so it should be equal 1 and 4.
It doesn't say two integers though, right? So we're looking for a number. It could be 1/4 and 16, right? 16 times a quarter is 4.
Yeah.
So what do we know about these two numbers? Well, their product is 4. But if we want to do this, we want stuff in terms of one variable, so let's solve for y. So y will be what?
4 over x.
4 over x. Okay, so the product we're looking for, or the sum of, the sum, right? We're looking for a sum of squares. So let's pop over here and say the sum of the squares will be x squared plus 4 over x, quantity squared. Okay, which is x squared plus 16 over x squared. Which is pretty easy to find the derivative of, right? So let's do that. So what's the derivative? Might want to rewrite it like that. Yeah, it makes it a little bit easier, right? That step, and then we'll do. So what's s prime? -3, yeah. Okay, so then we want to take this and we want to find the critical numbers, right? So in order to do that, we're looking to pull out the factor, greatest common factor. So it's going to be a 2, right? And an x to the -3. Okay, so take out the lowest power of x. So to get 2x, we're going to have to multiply 2x to the -3 by x to the 4th, and then we're going to have -16. Huh? Nice difference of squares there, right? Okay, so we've got 2x to the -3, or we just write that as 2 over x. Well, let's just do 2x to the -3. Let's keep that going. X squared plus 4 and x squared minus 4. Okay, so just factoring the difference of squares, and then x squared minus 4, yet another difference of squares. And factor that. X plus 2, x minus 2, and a little bit of cleanup. So 2, x squared plus 4, x plus 2, x minus 2, all over x cubed. Okay, so now we can do critical numbers. So what are the critical numbers? So it can't be 0, right? 0 will get undefined. Okay, so critical numbers. Flashing lights. 0. What else? Plus or minus 2. Okay, so if we're going to look at this, we need to look, when we're doing a max-min problem, we need to examine each of the critical numbers to see if they could be the max or the min, right? Now, in this case, we're looking for a minimum, right? So we got to look at the critical number and say, all right, is there a max or min there, or what's going on there? We also need to examine boundaries, right? And in this case, there are no boundaries, right? The numbers can be any real number. But if there's a problem, you know, it's dealing with time or something, then boundaries would be, well, you go from a time of 0 to a time of whatever. And we have to examine the boundaries to see if they could be the max or the min, right? Remember back a long time now, when we did look at boundaries and we were looking for an absolute maximum, we said, well, you look here, but you also have to look at the boundaries. So the same thing applies in a max-min problem. Okay, so we got the critical numbers. So how do we find out whether those are max or min or what? What?
Sine table.
Sorry, what? The second derivative. Ha! That's an idea, right? Because if we do the first derivative, we're going to have this big table full of, and there's a lot of factors, all right? We got a 2, we got an x squared plus 4, we got an x plus 2, we got an x minus 2, and we have an x cubed. And we've got intervals below -2, from -2 to 0, from 0 to 2, and from 2 beyond. And it's going to make a really big table, right? But we have the second derivative test, right? So what we need to do, this is why I strategically left a blank right here. Wow. Because you're not going to do the second derivative from this, right? You do the second derivative from here. Okay, so let's just move it over here. I'll just rewrite it because some of you might be. So what's S double prime? You're all writing it down, I'm sure. 2. Oh, 96. 96 x to the -4. So we can just say it's 2 plus 96 over x to the 4th. All right. So we got 3 critical numbers to, but what do you notice? What's this going to be? 2 plus 96 over x to the 4th is always, if it's defined, so we can't do a 0 in it, right?
Yeah, it's always positive.
It's always positive, right? If this is defined, so it doesn't exist, so d n e when x equals 0. All right, now in the context of the scenario, what happens when x equals 0? I mean, you can't have, 0 can't be one of the numbers, right? Because you can't do the reciprocal of that. All right, so we don't need to worry about 0. That's not one of the numbers, right? Like what's going on there? If we were to graph this, it would be an asymptote, right? Okay. We're not graphing, right? If we were graphing, we would be doing the first derivative test, right? Intervals of increase, decrease. But we don't have to. So we can say for this, well, S of 2, well, S double prime is always positive. When x is not equal to 0. Really, we should have gone up here somewhere and probably said x can't be 0, right? That's really a restriction on the domain. That should have been an initial position. Hey, it can't be 0. Should take reciprocal. Okay, so if S double prime is positive, then that means that it's what? Concave up, which means that there is a minimum. So there will be a minimum at -2 and at +2. Cool. Now we just got to plug them in and see what the numbers are. So if x is 2, excuse me, if x is 2, then what's y? 2. And if x is -2, then what's y? -2. So the numbers are, what does it actually ask? Determine 2 numbers whose product is 4 and whose sum of squares is a minimum. Okay, so the numbers are 2 and 2, or -2 and -2. Okay, and then look back, do they meet the criteria? It didn't say positive integers or anything, right? So we've got 2 sets of numbers. Does it meet the criteria? 2 times 2 is 4. Is there sum of their squares a minimum? Yeah, it's going to be. Okay, questions? And we saved ourselves making a big chart full of, stuff that really we didn't need. Now, what I would say is, do second derivative, right? So look at your first derivative when you've done it, right? We're going to kind of leave that sitting there, and maybe what we'll do is we'll just say, let's done the first derivative, it's easy, let's do the second derivative. Okay, then we'll pull apart the first derivative, well, we'll find all the critical numbers, and now we've got the second derivative. But if the second derivative isn't easy to find, then we might just do the first derivative and just say, yeah, you know what, let's just wait and see what happens, and then we'll decide, are we going to go find the second derivative, or maybe we just look at it and say, you know what, we can do first derivative test on this, it won't be that onerous, right? Here, there's a lot of factors, so. 2. If 2,700 square centimeters of material is available to make a box with a square base and an open top, determine the largest possible volume of the box. Okay, so then what we should do is, let's start with a diagram of an open-topped box. I had one here. Yeah, I know, I was going to show you, but what's the box? Look, here is an open-topped box, right? So you think about it, what happens? What I would do is cut along these edges and just fold down the flaps. Okay, so what's it going to look like? Well, the box has a square base. So let's start off with a diagram of a square base. And it's the base, so we will call it B, but then off of each base there is a little flap. And these guys will fold up and make, a little too big, and make the open-topped box. So we'll call this B, and we'll call this H. Okay, what's the volume of the box? This box. What is the volume of this box? B by B by H, right? So volume is B squared H. Okay, so that's a problem because there's two variables, right? So we got to see, can we get this down to one variable? So is there any other information here? Yeah, the total area. Okay, well we can work that out, right? Because this thing is made up of 5 pieces, right? So let's come up with an expression for the area of the box. So the area is B squared plus, and how big are each of these guys? 4BH. Okay, now what do we know about the area? We know it's 2,700. So we're going to plug a 2,700 in, and we are going to solve for H, right? If we do that, then we'll have H in terms of B, we'll plug that into the volume, we'll have one variable, and away we go, right? Off to the races. Okay, so what do we get? Well, we'll get 4BH is 2,700 minus B squared. So H is 2,700 minus B squared over 4B. So now we can go over to our volume expression. We can plug in. So V is equal to B squared times 2,700 minus B squared over 4B. So we can cancel a B out, right? Now we can multiply this out. So 2,700 divided by 4. 2,700. So that's what, 6 gives me 24, and we got 30, which is 7, and 22, 675. So this 2,700, so we got a B times this, which will be 675B minus, okay, we've got B times B squared over 4, so minus B cubed over 4. Okay, and that's not such a bad way to write it, because that's easy to do the derivative, right? Now we just do the first derivative. So, what's v prime? Minus. Okay. Is it okay?
Yeah.
Okay. Can we do v double prime pretty easily at this point? Yeah, okay, so we might as well, right? Say, hey, we're going to have to test this out. Oh, now before we go any further, I should back up because I keep forgetting to do the first part, which says that we're dealing with this volume of a box, and we've got 27, we've got stuff that we know about the volume. Well, let's do it now, I guess, right? We know the volume. Or do we want to do this? Let's do the second derivative. So what's that going to be?
0
Negative 3 halves.
Negative 3 halves b.
about the volcano.
Okay, wait, now what do we know about b? I mean, it can't be negative, right? So b has to be positive. So the second derivative tells us that if b has to be positive, then negative 3 halves b has to be negative. And if it's negative, then it is concave down and has a maximum. All right? So from this statement, right, so, we can say, well, we know b has to be greater than 0. So negative 3 halves b will be less than 0, which leads to concave down, which leads to a maximum. All right, cool, right? It saves some work, because we know if this thing, it's going to have a maximum when we figure out the volume. All right, so now we need the critical numbers. Okay, so let's take our, no, not right. No, that's right, okay. So we know that v, we know v is greater than or equal to 0, right? The volume has to be greater than or equal to 0. You can't have a negative volume. Which means that 675b minus b cubed over 4, so that's our volume, right? Has to be greater than or equal to 0. So what we want to do is figure out the limits, right? Like what's the lowest value for the base, what's the highest, right? So we need the extremes because we're going to be working in a certain interval here. All right, so multiply through by 4, we get 2700. B minus b cubed is greater than or equal to 0. Factor out of b, or just divide out of b, really, right? You can divide that. So 2700 minus b squared is greater than or equal to 0. So then b squared, we move that over there, make them both positive. So b squared will have to be less than or equal to 2700. Excuse me, right? Just subtract 2700 from both sides and then multiply it through by -1, which is going to flip the inequality and make everything positive. And what's 2700? So it's 900 times 3, so it's 30 root 3. So b squared, b, hang on, square root both sides. So b is less than or equal to the square root of 2700, which is 330 root 3. So we know that b is in a range from 0 to 30 root 3. So these are our extremes, right? And then we can kind of reject them. I mean, if b is 0, what's the volume? 0. If b is 30 root 3, then b has used up the entire thing, and then what's the height? If b is 30 root 3, you know, the height, 30 root 3 is 2,700, right? So then h will just be 0, and we'll have a volume of 0. So we need to look at them but reject them, right? So we're rejecting either of those. So now we go to the first derivative and say, all right, when you're 0, that's the critical number. That's going to be it. And we know that at that critical number, it will be a maximum. Okay. So, so 0, so the critical number, let's do the critical number. 0 is 675 minus 3b squared over 4. Multiply through by 4. 2,700 minus 3b squared. 3b squared is 2,700, b squared is 900, and b is equal to 30. Right? It's really plus or minus 30, but we're rejecting a negative. We know that b has to be positive. But we can write that in, sure, plus or minus 30. Okay, so we know b is between 0 and 30 root 3. When b equals 0, v is equal to 0. When b is 30 root 3, then h is equal to 0, which means our volume is 0, right? Because we have to examine not only the critical numbers, at least the one that applies, so negative 30 doesn't apply as a critical number, it's just positive 30. We have to examine these two guys, right? Because we don't know what this thing looks like. Well, we do, sort of. Therefore, there is a maximum when b is equal to 30. Now, it probably asked us what? Determine the largest possible. So we need the volume. So we got to figure out when b is 30, what's h, and then we got to plug in b squared h and work it out. Okay, so at this point, okay, how do we know it's a maximum? Because we did the second derivative, which was always negative, right? Because we know that b has to be positive, so this has to be negative, concave down, maximum, right? We don't have to do the first derivative test on this. Okay, so when b equals 30, h is equal to 2,700 minus b squared over 4b. 2,700 minus b squared over 4b. 2,700 minus 30 squared over 120. 30 squared is what, 900?
Yep.
900, so 1,800 over 120. 15? I think you're right.
Yeah.
Yeah, 12 times 50, yeah. Cool. It's going to make the volume easier to work out. So v is equal to b squared h. 30 squared times 15. 900 by 15, so that's 9,000, and then half of that, 13,500. What units? Is it centimeters? Yeah, square centimeters, so 13,500 cubic centimeters. And is there anything on there you need to see? You may want to go back and rewrite your notes, putting them in some logical order. Determine the point on the curve y equals x squared that is closest to 18, 0. All right, let's draw a picture. What are we dealing with here? So we've got y equals x squared. And we've got the point 18, 0. Right? So here's 0, 0. So, I mean, here it's 18 units away. Right? Then we've got like the point 1, 1, 2, 4, 3, well, in that case, 18 is like way out here. Okay, so there is some point on this curve that is closest. Yeah, we got to figure that out. Yeah. Okay. Okay, so what do we need? We need an expression for the distance between these 2 points. So if we do that, so first let's give this point a name, which is xy. But really it's not xy. What is it? It's x and what's the y equal to? X squared. So this is really the point x squared. Okay, because it's on y equals x squared. It's on that quadratic. So this is x, and this is x squared. So this distance here is, and it's a right triangle, right? Because you've never done the distance formula, right? I know, it's amazing. And then we hit math 31 and finally figured out how to get the distance between people. It used to be covered in grade 10. All right, so it's just going to be 18 minus x. Okay, so we'll say d squared is equal to 18 minus x squared plus, what's this guy going to be? So how high is this?
X squared.
X squared. Just x squared. Yeah, x squared squared, but it's x squared squared, right? This is really like x squared minus 0, this distance, but it's just x squared. Okay, so we got x squared squared. So what are we going to do with that? We are just going to, we're going to do this. We're going to call it big D. Okay, so if we want to get closest to, so if we minimize little d, which is actually the distance, right? Little d is actually the distance, then d squared will also be a minimum, right? I mean, if you've got the smallest value of d you can get, then when you square it, you've still got the smallest value that you can get. And this way, we don't have to do a derivative of the d squared, right? We're just going to do d prime. We're going to minimize d prime, or d, big D. We're going to minimize big D, which then allows us to get little d. Okay? And not have to worry about, oh, now I've got like 2d, d, you know, whatever, right? Okay, so let's just expand this. We get 18 squared. Anybody know that offhand? Okay, it's 324.
Oh, of course, how silly of us.
Well, some people might know their 18 times table.
I don't know my timetables. 3.
Minus 36x plus x squared plus x to the 4th. Okay, so let's rewrite that in a nicer order. In other words, descending powers of x. So I think we could do d prime, and then I know we could do d, the second derivative, d prime prime, right? Because that's easy to do. It's just a polynomial. So first and second derivative will be very straightforward. Okay, what can you say about the second derivative? It's always positive, right? I mean, it's vertically stretched by a factor of 12 quadratic moved up 2 units. It's always positive. So if it's always positive, so always positive, which means that it's concave up, which means we have a minimum. Okay? So whatever we find when we, well, then we just need the critical numbers for 4x cubed plus 2x minus 36. We know our x value has to be greater than 0, right? Because it can't be lying on this side. It's got to be the closest distance, so it's got to be over here. Okay? I mean, we could say that if we want, x is greater than or equal to 0, because if you're moving out here, you're just moving further away. Okay, so let's take our d prime. Okay, so the critical numbers, let's do, say we're going to do critical numbers. 4x cubed plus 2x minus 36 is equal to 0. I don't think we can just straight out factor that, right? So we need an integral 0.
Divide out of 2.
Divide out of 2, sure, let's do that.
Yay.
2x cubed plus x minus 18. Okay, so if x were what? 2 gives us 9. 2 cubed is 8, 16, 18. Yeah, if x is 2, so when x is 2, and here's the thing, we'll always make sure we give you an integral 0, right? So like 1, 2, 3, God, we're negative 1, negative 2. Yeah, it's going to be, so we know that
X minus
x equals 2 is a 0. So we divide, what do we got? 2, 0, 1, negative 18, negative 4, or sorry, wait, no, that just comes down, right?
Yeah.
It's been a while. 2, negative 4, 4, 8, negative 8, negative 9, 18, 0. Right, good. So we've got,
No.
no?
It'll be 2490.
2, 4, oh, 9, right, positive 9. That's it, told you it's been a while. Okay, so what do we got? 2x squared plus 4x plus 9 equals 0. All right, can we factor that?
2x plus 3 2x.
I don't think so. Quadratic formula. QF negative b plus or minus square root of b squared. Wait a sec, wait, there's something I just taught the 20s the other day. If a is positive and c is positive, right? Then b squared minus 4ac could be negative, and in this case it will be because b squared is 16 and 4ac is going to be like 72. Okay. So b squared minus 4ac is less than 0, no real roots. Okay, so what's the other factor? X equals 2. That's it then. Yeah, x equals 2. So this means that therefore x equals 2. Remember, x equals 2 is a 0 of this, right? So the only 0 we have is x equals 2, right? It's a 0. This guy, quadratic formula, the discriminant is negative. There's no real roots. So x equals 2 is a minimum. So the point 2, 4 is the minimum distance from 18, 0. So 2, 2, 4 is the closest point. To 18, 0. Okay, and you could work out that distance, and you could do like 2.1 and whatever that was, and 1.9, and say, oh, they're bigger. It could be a larger value. Cool. Next. Determine the radius and height of the right circular cylinder of largest volume that could be inscribed in a right circular cone of radius 6 centimeters in height. I'd like to read that fast because it's just you really gotta take this slow. What's going on here? So we're trying to put a cylinder inside of a cone. Okay, so we've got a cone. We want to put a cylinder inside. So let's do a cross-sectional view, right, running through the middle of everything. So cross-sectional view of a cone is a triangle. And the cross-sectional view of a cylinder is a rectangle.
Maybe not.
Well, maybe it's square, maybe it isn't. I don't know, but we can't say that it is.
Looks pretty square to me.
Yeah, but that's a lousy diagram. Remember, didn't we ever tell you this, like in grade 10? Diagrams are only placeholders for information. They're not necessarily to scale. Right? It's like Don't sit down on a trig test in grade 10 or something or 11 and try and measure it with a protractor and a ruler. It's not going to work.
So I got it 0 to 10.
Okay, what do we know? So the cone has a radius of 6 centimeters, and the cone has a height of 10 centimeters. Okay, so if we pull out just 1/2 of this, right? Just say, here's what we're going to look at. We're going to look at a triangle, which is 10 centimeters here and 6 centimeters here. And inscribed within that is this cylinder, right, whose height we will call h, and whose radius we will call r. And that makes...
very inventive claims, are we?
Yeah. So, okay, hang on, let's do this. So this is 10 centimeters out here. So this is h. So what's this? Ten minus h, right? So I think we've got some similar triangles. Right? We get this little triangle here, which is 10 minus h and r, and we get the big triangle here, which is 10 over 6. Right? So 10 minus h over r, this ratio, will be equal to 10 over 6. Right? Little triangle, big triangle. Okay, so we can work on solving this. So we got 60 minus 6h is equal to 10r. And we'll solve this for h in terms of r, right? So we'll get h, so 6h will be 60 minus 10r. And h is 10 minus 5/3 r. So we have an expression for the height in terms of the radius, right? Because we want the right circular cylinder of largest volume, right? So it's the volume of a cylinder we're trying to maximize. So V sil, what's the volume of a cylinder? Area of the base times the height, the base is circular, pi r squared h. And that's on your formula. No hiding. Okay, that's the thing we want to maximize, the volume. So V is equal to pi r squared, and h is 10 minus 5/3 r. And what do we know about our radius of the cylinder, right? So the cone is 6 centimeters, so the cylinder radius could be anywhere from 0 to 6. Right, I mean, it could be here. Now, it can't be 0 and it can't be 6, right? Because there'd be no volume. So if it were 0 or 6. So we know that r is between 0 and 6. And we know that r can't be 0 or 6.
So I didn't put that equal.
Yeah, but we're still going to put it. Because r, it can be, okay, we'll say, if r equals 0, then v equals 0. And if r equals 6, then v equals 0. Okay, so we'll leave that. It's clean, right? Because those are extremes, right? And we do, when you're doing a max-min problem, right? I mean, 99, I don't know, some certain percentage, 78.2% or some number of all statistics are made up on the spot. Some certain percentage of max-min problems, and it's fairly high, it's in between. But then you've got the odd one, which if you're not looking at the extremes, it will come back and bite you because it really is a max or min at the extreme. So you need to examine them, and this is the examination, right? Hey, if it's 0, you can't do it. If it's 6, you can't do it. Okay. So what we find is what we want. All right, so let's clean up the volume thing here. Multiply through by pi r squared. So let's call that 10. Pi r squared minus 5 pi r cubed over 3. Okay, now pi is a constant, right? So derivative, easy. How about second derivative? Easier, right? First derivative is easy, the second derivative is easier. Now 20 pi minus 10 pi r could be positive, could be negative, right? So we don't know, right? We're actually going to have to find the r value, or r, the critical numbers for v prime, get those r values, and as long as they're not 0 or 6, then we'll plug them into the second derivative and say, all right, it's positive or it's negative, and therefore this. Right, the other couple, it was just, hey, that's always negative or that's always positive. This one could go either way. Okay, so critical numbers. Uh, 20 pi r minus 5 is equal to 0. All right, so now you do a little factor magic, right? So what do we got? 5 pi r. 4 minus r. So either r is 0, right? Which we don't need to check because we rejected that. If your radius is 0, your volume is 0. So r equals 0, or r is equal to 4. Okay, this previously rejected. Okay, so we don't need to do that. So we need to look at v double prime at 4. And what can we say about this? It's 25 minus 45 is negative, right? Negative. If it's negative, then what? Negative 20 pi, so it's concave, which means there is a maximum. Okay, were we looking for a maximum? Yes, right, so the largest volume, a synonym for maximum. That could be inscribed, so determine the radius and height. We have the radius, and we've got an expression for height. Okay, so h is equal to 10 minus 5 times 4 over 3. So that's 10 minus 20 thirds, which is 10 thirds. Right, let's put it all together. So 30 minus 20 over 3. So the radius of the cylinder is 4 centimeters, and its height is 10 thirds of a centimeter.
Close enough.
3 1/3. Okay, just gonna keep going. Well, there's 7 that we need to do either today or today and Monday. So whatever we can get done today. And then you can start in on the problems because you're going to see very similar problems in the first bit of the exercises, right? And then if we get all 7 done, then Monday's just work period. And if we don't, then we just finish off whatever. 24 minutes. Well, we'll get at least this done. A window consists of a blue semicircular section surmounting a clear rectangular section as shown below in black and white. The blue glass lets through half as much light per unit area as the clear glass. Determine the radius of the window that admits the most light if the perimeter of the window is k meters. So we can't actually solve this and get a number, right? We're not going to end up with, so r is 3, right? What we're going to get is r in terms of k, or k and p, right? So it may have something to do with the variables. And all this, it's just a more generalized question. A more specific question would be, something about, I don't know. All right, so what we're going to do is this. We're going to let p be the amount of light. Okay, so we want the most light, right? That's what has to be maximized, is the light. So that's what P is going to be. Let P be the amount of light. Per square unit of blue glass. Okay, and then we know 2P will be the amount of light coming through the clear glass. Okay, so we've got P, which is the amount of light coming through, and we've got K, which is the perimeter, and K is fixed, right? So P and K in this problem, they're constants. Okay, P and K are constants. We're keeping the perimeters fixed at K. We don't know what K is, but we know K doesn't change. So it's the R that we want to change. Okay, so the light that comes through is going to be P times the area of this, right? So the P, little p is the amount of light per square unit of blue glass, and that's a semicircle, so it's 1/2 pi r squared. And then we've got the rectangle. Now, what does the rectangle measure? Okay, so hang on a sec. So we've got a radius here. This is r. So this is 2r going here. It's a rectangle. So we could call this, I guess this would be h. And this would be h for the height of that rectangle. And this here, that arc, that's half of the circumference, right, which is 2 pi r, so half of 2 pi r. So this will be pi r. Okay, so that means that K is equal to, so K is the perimeter, right? So K is equal to 2r plus 2h plus pi r. Okay, okay, but we can't have all these variables, right? So what we're going to do is get h in terms of k, because k is something that we know, right? K is part of the question here. So 2h will be k minus 2r minus pi r, and h will be k minus 2r minus pi r over 2. Aren't nice generalized questions are really nice. So we've got the light coming in through the blue semicircle. Now we've got twice as much light, so 2p coming in. Now what's the area here? It's going to be 2rh. Because that's the area of the rectangle. Okay, so now we got to go in and we've got to substitute for h. Well, let's do a little cleanup first. So let's go, it's p over 2, right? Because remember, p is a constant, right? So p over 2 is going to be a constant. Now we've got pi r squared. And here we've got 4p r h. And now we're going to substitute for the h, the k's, and whatever else, right? So we've got p over 2. How can I write that? P over 2 plus 4pr, and we've got k minus 2r minus pi r all over 2. Okay, so that's a 2. P over 2 pi r squared plus, okay, what do we got? krp, 2krp, or kpr, minus 4pr squared minus 2p pi r squared. Okay, it's messy, but it's very easy to differentiate. So remember, k and p are constants, right? So p over 2 pi is a constant. So we're just really worried about the r squared, which is going to be 2 times r. and the 2 will take out the 2 on the bottom. Okay, so L prime. So the 2 multiplies this, gives me a p pi r. 2kp is a constant, so there we go, 2kp. 4p is a constant, so minus 8pr. 2p pi, 2p pi. 4p pi r. 4p pi r. Anything collect there? Oh, we got p pi r's, right? Yeah, so we can combine the p pi r. So negative 3 p pi r plus 2kp minus 8p r. Okay, can we do the second derivative easily? Yeah, if you can do the first derivative, you know, easily, then you can do the second derivative, right? I mean, so this will just be, so L double prime is negative 3p pi, that's a constant, minus 8p. So what can we say about the second derivative? It's always negative, right? Because p has to be positive, okay? So p, k, and r are all positive, right? I mean, p, k, and r are all positive. Okay, so this L double prime is negative, which means that it's concave down, which means that we have a maximum. Okay, this is nice. Last year I did all the charts. Right. So first derivative, I don't have to do that anymore. Okay, that's gonna take me. I want another page, I think. So hang on, let's just go. Insert blank page. Now is it the right spot? Yes. Okay, so where were we? So critical numbers. So L prime exists everywhere, right? There's no radicals, there's no denominator. So we want 0 to equal negative 3 pi r minus 8r plus 2k. And we want to solve this for r, right? So, move those over. 3 pi r plus 8r is 2k. R, 3 pi plus 8 is 2k. R is 2k over 3 pi plus 8. And that is the solution. Right? That's what your radius is, right? That's the only critical number. And k really is the, k is a constant, and 3 pi plus 8 there is a constant. Okay, so the most light is let through. When r okay, so if somebody were actually figuring this out, if they're writing a computer program for whoever makes Windows and stuff like that, and they would have these different values, right? Whoever programmed it has to know the calculus in order to be able to come up with an expression for the maximum, right? So they have to work through this, come up with that. Then they can just program that into a spreadsheet or into just a little app or something like that. And you can come up with the answer. Boat A, David's favorite question, boat questions.
Yeah.
Boat A is 40 kilometers west of boat B. If boat A sails east, so it starts moving towards boat B, and boat B, starting at the same time, sails north to attempt to get away from boat B. Determine the time when the boats are closest together. Okay, it's picture time. Okay, there's B, there's A, this is 40 kilometers. A is going to move at 20 kilometers per hour, so let's say 20 times t. And B is going to move at 10, let's call this 10t. And so there's some point here where they're going to be closest together, and that will be the distance between them. And I guess we should finish this. So this is 40 minus 20t, that distance. Okay, so what we're going to do is, because I've stuck a t in there, we got to say what t is. So let t be the time in hours since the boat's sailed. So the distance, well, d squared is equal to 10t quantity squared plus 4t minus 20t quantity squared. Okay, so we can work that out, right? Just get an expression. So d squared, got 100t squared plus 1600 minus 1600t plus 400 t squared. And collecting together. Now, if we want them the closest together, we want d to be little d to be a minimum. We're just going to let big D be the distance. We'll worry about it because if it's a minimum, then so is little d. Okay, so d prime, d double prime, easy to work out. 1000t minus 1600. So what can we say about d double prime? It's positive, which means that it's, right, positive. Concave up. Minimum. Good. That's what we want to find, right? We need a minimum. So it's all the minimum, really. I mean, it's just a quadratic that opens up, right? So. Okay. So then we need the critical numbers. So d prime critical numbers. So d prime is 0, so 1000t minus 1600 is equal to 0. 1000t is equal to 1600, t is 1.6.
I just supposed to have that in a fraction or use it as a decimal?
Yeah, okay, you're right.
No, just curious. I'm not trying to raise issues.
No, I was just looking at my notes there to see, yeah, I had it as 8 over 5. 1.6 is exact, so it's not so bad, right?
Yeah.
You know, if it's like 8 over 3, you leave it as 8 over 3. So what were we supposed to find? Determine the time when the boats are closest together. Okay, so are there any other critical, there's no other critical number, right? That's just it. So the time when the boats are closest together is the time when the boats are closest together is 1.6 hours after they set sail. Okay, and I don't think it asked us for the distance. Nope. We could work out the distance. Now, there's one thing you should examine. Maybe we should work out the distance because we know that right now they're 40 kilometers apart. What if they never get closer together than 40 kilometers, right? So I think we really should throw in the 8/5 and work out the distance just to make sure that, hey, what if it is just getting bigger than 40 all the time, right? Then, so that's part of checking the extremes, right? Because we know our time has to be greater than or equal to 0. If the time is 0, they're 40 kilometers apart. After that, they both start moving. What if they never get closer together than that? So D is equal to, so what do we got? 40 minus 20 times 1.6 squared plus 10 times 1.6 squared. So I'm just going to give you the numbers. Works out to 8 and 16. So that works out to 320. And the square root of 320 is less than 40, right? Square root of 320 is 20. It's less than 30. Okay, so this is less than 40. So 1.6 hours. Period. We do this?
No.
I don't.
Time.
There might be, there might not be.
Why risk it though?
Yeah. Well, last time I did this, I took 3 pages. But last time I did this, I did all of the, I did all the boundaries. Like I evaluated the value at 0 and at here and at there, because I was dumb. So. You know what? At the very least, let's start. We'll get as far as we can if we have to stop. I mean, what else are you going to do this period, right? But we want to work.
That's the dream.
Yeah. Well, you will not be living the dream. I shall make no comments about your hockey team because they won yesterday.
They did win yesterday.
They probably outcoursed you 2-1.
Next one.
You
Desperately.
Yeah. I don't know if my kid did a stats recap. I'll have to look online and see.
Tell her to stop slacking.
Oh, she probably did. I said I don't know. Anyways, all right. So we got cable TV companies laying cable in air with underground utilities. 2 subdivisions, P and Q, are located on opposite sides of Willow Creek, which is 100 meters wide. How many creeks that are 100 meters wide?
Really a creek.
Yeah, let's call it Willow River or something. I don't know. Opposite sides of Willow Creek, which is 100 meters wide. The company has to connect points P and Q with cable, where Q is on the north bank, 1,200 meters east of P. Okay, so here's Q, and here's P. Well, let's put P a little further out. And here's P, and this distance is 1,200 meters. And this distance, well, we already know that's 100 meters. Okay. What else do we have? Company P. It costs $40 per meter to lay cable underground and $80 per meter to lay cable underwater. Determine the least expensive way to lay the cable. So you think about it, they could lay the cable here and then just go underwater, right? So that's your maximum would be, or probably your maximum would be 1,200 times 40 plus 100 times 80, right? Or you could do that the same. So there's some part where if we go some distance underground and then cut across, we're going to have a minimum cost. Okay, so we're going to say, all right, let's say you work your way to here. And we'll make this distance x. We'll call this distance y. That'll make this distance 1,200 minus x. So we're going to lay cable 1,200 minus x meters underground, and then we're going to go and cross the river and lay y meters of cable across the river at a certain angle. Okay. So least expensive way to lay the cable. So we'll let C be the cost of laying the cable. Now we know that x is anywhere between 0 and 1,200. Okay, so we can lay 0, we could just go straight across. So that would be, this would probably be the most expensive way, right? If you just laid it straight underwater, that would be the most expensive one. Okay, so the x value can be between 0 and 1,200, right? We know that y squared is equal to x squared plus 100 squared. Okay, just Pythagorean theorem in there because we want to get y. Well, we don't want y, we want just x. So y is equal to the square root of x squared plus 10,000. Okay, so now we've got an expression for y. The cost is $40 for each of these meters, so the cost is 40 times 1200 minus x plus 80 times y. Why I put that in parentheses, I don't know, but now we're going to replace the y. So we've got 40 times 1200, which is 48,000, minus 40x plus 80 times the square root of x squared plus 10,000. So that's going to be our cost for laying the cable, right? And we want to minimize that cost. So we'll start by taking the first derivative. Negative 40. So I'm going to give it to you, okay? Let's just see. Maybe we can push through. Okay, so there's the first derivative. Okay, so negative 40 plus 80x over, or the square root of x squared plus 10,000. Second derivative, I don't think I want to do that just yet. The first derivative exists everywhere, right? Because we know that x has to be greater than or equal to 0. So what do we want? We want to set this equal to 0 plus 80 over, let's go over here, so we get 40 times the square root of x squared plus 10,000 is equal to 80x. It's an x. So square root of x squared plus 10,000 is equal to 2x. I'm going to extend the page. Okay, so that means that x squared plus 10,000 is equal to 4x squared. Okay, so we square both sides. 3x squared is equal to 10,000. X squared is 10,000 over 3, and x is the root of 10,000 over 3, which is 100 over root 3, or 100 root 3 over 3. Okay, let's copy that down. I'm just going to finish it off. Okay, because whether the cell goes or not. Now what we should do is test all of the values, right? So instead of worrying about, well, I think we can do first derivative test on this. So first derivative test, extend the page, it's just going to be a long page. First derivative test is going to, so f dt, we got 0, we got 100 over root 3, and we've got beyond, and c prime will be negative here, positive here, this, we have a local min. Okay, so we have a local min. Is it the absolute minimum? Well, we would have to take x be 0, so the cost of 0, which is equal to ... 56,000. Okay, give me 2 more seconds, I'll just write out the rest of it. The cost of 1,200 would be 96,333, and the cost of 100 over root 3 is equal to 54,928. Okay, so the amount of cable you would lay underground is 1,200 minus 100 root 3. Okay, so the amount of cable underground is 1,200 minus 100 over root 3 meters. Okay, so what I'm going to do is just fill in the rest of this. You can go. I'm going to fill in the rest of it, and then I'll stop the video, and then I'll put this up as 1 to 7, and it'll have in the filled-in values for there. So, yeah, we kind of push 7 quick, but
I warned you. You were warned.
yeah. I said don't do it.
Well, it's only our education.
Yeah. Out of it.
And 1200 is 40 times 1200 minus 1200. That's 80. Plus 10,000. 96,333. And done.